So in this problem we have a beam that goes from point A to point C, and along this beam we have at point A we have a pin joint, alright, and at point C we have a roller. Alright, and then from point A to point B we have a distributed load. It's equal to a constant 2 kilonewtons per meter, and then at point B we have a couple moment of 50 kilonewtons per meter. Alright, and then the total length of the beam is 10 meters. From point A to point B is 5, and from point B to point C is 5 meters. So for this given condition for the beam, we're asked to determine the shear and moment diagrams for it. So, so what we have here is we have so we're going to draw, first step, we'll draw a free body diagram of ABC. So if we have at point A, we have a pin, so we'll have A of Y and we'll have A of X. Along the point A to point B, which we know is 5 meters long, we have a distributed load of 2 kilonewtons per meter. And at point B we also have a couple moment of 50 kilonewtons per meter. And then at point C we have a roller. Alright, so we'll have NC. Alright, or you could say CY. So alright. So we'll use CY. Alright, so so to find our three unknowns, A of X, A of Y, and CY, we'll use our three equilibrium equations. So we'll start off with the easiest one. We'll assume our forces in the X direction and set that equal to 0. So the only force we have in the X direction is AX. Therefore, AX is equal to 0. Alright. For the second part of the problem, we will sum the moments about point A. Alright, so we'll sum all of our moments about point A and set that equal to 0. If we do that, we'll end up getting a negative moment due to our distributed load. So we'll say that our distributed load has a magnitude of 2 kilonewtons per meter times 5 meters. Alright, that'll give us the concentrated force due to that distributed load. Alright, which is just equal to the area under the distributed load diagram. So since we have a rectangle, it's just the intensity of the distributed load times the length, and then we multiply that by the centroid of our distributed load, x sub c. Since it's a rectangle, it's just going to be equal to half the length of the distributed load. So in this case, it would be equal to 2.5 meters. Alright. And then we have to add the effect of the couple moment. So we have the couple moment is equal to 50 kilonewton meters, and it's going along, it's rotating clockwise, so it'd be negative. So we have to add the negative 50 newton meters to our summation. Alright, and then the last thing we have to do here is we have to include the moment due to the roller force, Cy, and multiply that by the total length, which would be equal to 10 meters. Alright, so we can rearrange and solve for C of Y. If we do that, we end up getting C of Y is just equal to 50 kilonewton meters plus 25 kilonewton meters divided by 10 meters, which is just equal to 7.5 kilonewtons. Alright, and then to find A of Y, we just have to sum all of our forces in the Y direction. So that equal to 0. If we do that, we get A of Y minus 2 kilonewton meters times 5 meters plus 7.5 kilonewtons. So we would end up getting A of y is going to be equal to 10 kilonewtons minus 7.5 kilonewtons, or it's equal to 2.5 kilonewtons. Alright, so that's the first step done. We were able to solve for all of our reaction forces. Alright, so once we have all the reaction forces are now known, we can now draw our shear diagram and our moment diagram. Alright, so the first thing I'm going to do, just to make it very easy to see, is I'm going to draw the free body diagram again of our system. Alright, so here's our system. At point A, we know now that we have just an applied force of 2.5 kilonewtons. We know this is AY. We know along the section we have a distributed load of 2 kilonewtons per meter. You know, at point B we have a couple moment of 50 kilonewton meters. Right, and then we have at point C we have a force of 7.5 kilonewtons. All right, so this is our free body diagram, just drawn again with all the dimensions and all of our forces written as known forces. All right, so what we're going to do now is we're going to first draw our shear diagram. All right, here's our shear diagram. So this is basically our y-axis is our shear force, so that'll have units of kilonewtons. All right, and a positive shear force will be going up, and a negative shear force would be going down. So our first so to draw a shear diagram, we know that the change in the shear force we know is equal to the integral of wx dx. All right, from one point to an end point. We also know that if we have a concentrated load, so if we have a concentrated force, we know that our change in V would be just equal to that concentrated force. All right, so along the beam from point A to point B to point C, we have both distributed loads and concentrated forces. All right, so to find V of x, we have to determine the impact of our concentrated forces and our distributed loads. So at point A, we have a concentrated force of 2.5 kilonewtons. So we're just going to add that 2.5 kilonewton force here. All right. And then from point A to point B, we have a distributed load. So we can say V of x, we're going to write as being equal to the current value of our concentrated force. So right now or our shear load. So we know it's 2.5 newtons plus the integral from our starting point, which is at x is equal to 0, to our end point. So our end point is going to be anywhere from point A to point B, so we'll just include this as being equal to x. And then we know that inside the integral is our distributed load. Our distributed load is equal to 2 kilonewton meters, so it's just a constant number. This is our W of x, and then we have dx. All right. So when we integrate, after we integrate this, what we end up getting is we get 2.5 kilonewtons minus, and this should be a negative number, sorry, minus 2 kilonewtons x times the, we integrate this, we get x, and we evaluate it from x to 0, so we just end up getting 2.5 kilonewtons minus 2 kilonewton meters x. Alright, and that's our equation. So what you'll notice is this equation is just an equation of a line where we have a constant times our slope minus a constant times x. So we have minus 2 kilonewton meters is our slope. So we'll draw a line that'll go from point A to point B. Alright, it's not very linear. Alright, where this line here is equal to this equation down here. Alright, and then along from point B to point C, we have no applied loads or distributed loads. So in that case, since we have no applied load, no concentrated loads, and W of x from point B to point C is equal to 0, essentially, we have no change in our shear moment diagram. Right, so it'll remain a constant, and then at point C here at 10 meters, we have to include our concentrated force due to Cy, and we'll add that up. All right. So Cy is equal to 7.5 kilonewtons. The height of this, of our shear diagram from 5 meters to 10 meters. If we plugged in x is equal to 5 meters into this equation, we would have gotten 2.5 kilonewtons minus 2 kilonewton meters times 5 meters. So that's just equal to 2.5 kilonewtons minus 7.5, or minus 10 kilonewtons, which is equal to minus 7.5 kilonewtons. Right. Alright, so that's how we could draw our shear diagram based off of this equation. So we have from 0 meters to 5 meters, we have an equation of a line that starts at 2.5 kilonewtons and ends at minus 7.5 kilonewtons. And then from 5 meters to 10 meters, we just have a constant minus 7.5 kilonewtons. Right. So once we have our moment shear diagram, we can then integrate it to find our moment diagram. So now we're going to draw our moment diagram. Alright. So for our moment diagram, we have it's a little bit odd in the sense that the traditional positive y-axis is actually caused by negative couple moments. So we'll write it as being our negative axis will be along the typical traditional vertical y-axis or positive y-axis. So this will be our clockwise moments, and then our negative y-axis will be our positive counterclockwise couple moments. All right. Other than that, it's not too different. So we know that a change in couple moment can be caused by two things. It can be caused by it's known to be due to it's known as the integral of the shear diagram along a certain length, and we know that a change in moment can be due to a couple moment. All right, so all right, so all right. So those two things are what we have to account for in our problem. So from point A to point, if we look at our diagram, from point A to point B, we have no couple moments that are being applied. Well, we have a couple moment at point B, but before we get to point B, we have no couple moments. We only have our shear diagram. So what we can do is we can, to find m of x along that point, you can just add in, we can say that this would be equal to MO, which would be the couple moments, so we have no couple moments, plus the integral from 0 meters to 5 meters of v of x. So v of x in this case we have already known above here as being equal to 2.5 kilonewtons minus 2 kilonewtons meters x, and we'll integrate that from 0. I said 0 to 5 meters, but I really should have said is 0 to x. All right. So for m of x, if we integrate that, we would get 2.5 kilonewtons x minus 1 kilonewton per meter x squared, and we'd evaluate both of these from x to 0 meters, so we would just end up getting 2.5 kilonewtons x minus 1 kilonewton meter x squared. Right. So that is a parabola function. So what this, and it's since there's a negative sign in front of the x squared term, we know it's going to be concave down. So what it'll look like is it'll look something like this. Okay. So all right, and then once we have that done, we have that from 0 to, so this is valid from 0 to 5 meters. We have to integrate now from, we know that at x is equal to 5 meters, we have a negative 50 kilonewton meter applied load, or applied moment. So we need to add that negative 50 kilonewton meters to our moment diagram. So since it's a negative 50 kilonewton meters and our negative axis is going along the positive vertical direction, I know that's confusing, but it will get added to our diagram here. So we'll add 50, we'll have our negative 50 kilonewton meters here. Alright, and then we will so after that, sorry, so after we add that, we will then take, we know at this point here, the moment, if we evaluated this equation at x is equal to 5, we would know we know this would be equal to 12.5 kilonewtons minus 25 kilonewtons, so it's equal to minus 12.5 kilonewtons. So that's what this value is here. Alright. Alright, and then we would add that 50 kilonewton meters up. So at this point we would have 37.5 kilonewtons. So we would know that m of x would be equal to our couple moment, or our value at that point. 37. So this is from 5 meters to 10 meters. We know it would be equal to 37 kilonewton meters minus or plus the integral of v of x dx from 5 meters to x. So if we do that, we would add our v of x along that from 5 meters to 10 meters, which was just the constant minus 7.5 kilonewtons dx. Alright, so if we integrate that, so this is just a constant number, you get 37.5 kilonewtons minus 7.5 kilonewtons times x from 5 meters to x, so we just end up getting 37.5 kilonewtons minus 7.5 kilonewtons times x minus 5 meters. Alright. So what this looks like here is we just have, again, we have a constant minus a linear term. So if we do that, we'll have a straight line that'll go from here to here. Alright. So this line here, would it be equal to 37.5 kilonewtons minus 7.5 kilonewtons times x minus 5 meters. Alright. So this would give us our moment diagrams as well. And then the last thing that I want to point out here is that you can solve for the magnitudes of the moments using the shear diagram here. So if you integrated, so let me use a green marker here. So if you integrated this region here, which is a triangle, so we know the area of this triangle is just equal to 1/2 the base times the height. We know that the height is equal to 2.5 kilonewtons, and we know that the base, we could solve for the base by setting this equation here equal to 0. So we know that v of x is equal to 0 at x is equal to 1.25 meters. So you could plug in 1.25 meters here. If you did that, you'd end up getting 1.5625 Newton meters, which would be the height of this section here. So this is supposed to be at 1.25 meters. This is supposed to be 1.25 meters here, and we know that the height of this would be equal to 1.5625. Alright, if we then subtracted the area of this triangle here, we would get the equivalent, you would be able to calculate the value of this number here. So we know that this would be equal to 3.75 meters times times 7.5 times 1/2. Alright, so we know that that would be equal to 14.0625 Newton meters. So if you subtracted 1.5625 minus 14.0625, you'd end up getting 12.5 kilonewton meters, which is what we got using our moment equation here. All right, and then the last thing we have is we could use the area under this last section here, which is just equal to minus 7.5 kilonewtons times 5 meters. We know that's going to be equal to minus 37.5 Newton meters. So we could have we would subtract that from this value here to calculate our moment at the end of our beam, which we know is 0 Newton meters. Okay. All right. So that concludes this example on how we calculate our shear moment diagrams from our initial conditions. So just to recap, we used our free body diagram to find our reaction forces at our two supports, A and C. Once we knew C of y and A of y, we could then draw our shear diagram and our moment diagram using the relationship between the distributed load, the shear force, and the moment force. All right, so we know that the shear force is just if we integrate the shear force, if we integrate the distributed load, we would get our shear force. And then if we integrate our shear force, we would get our couple moment. And then similarly, we know that if we took the derivative of our moment, we should end up getting our shear force, and we take the derivative of our shear force, we would get our moment. All right. So that concludes this problem on shear moment diagrams.